I want to look now at the phase and amplitude response of the position of an oscillator. So that is, we want to look at the steady state response, xp, as a function of the drive frequency omega. As we change the drive frequency omega, the amplitude will change and the phase will change, because the amplitude is given by this, which depends on the drive frequency, and the phase is to do with the argument of the mechanical impedance, which is again to do with the drive frequency. Now I've written it here in terms of the mechanical oscillator, but equivalently we could be talking about the charge on an electric oscillator, and we have the electrical impedance here instead, and the mass changes to inductance. The phase response is the same. So if we drive at frequencies well below the resonant frequency here being arbitrarily 100, the position is in phase with the drive. So the phase difference here is 0. As we increase the drive frequency, we come to a transition where the phase flips down through negative pi and 2 on resonance, and then down to negative pi for frequencies well above resonance. The different shapes here represent decreasing damping. So for large damping, we have a smooth curve. For very small damping, we get a very sharp curve. So phi is roughly 0 for frequencies much less than the resonant frequency, negative pi on 2 for frequencies at the resonant frequency, and negative pi for frequencies much larger than the resonant frequency. And for small damping, so when gamma is very small, the phase changes very quickly around resonance as you move the drive from below to above resonance. If we look at the amplitude response now, A, on a linear scale, we see something that looks like this, and it's not particularly useful. What we see is that for very low damping, that's just red curve, the amplitude on resonance is much larger than any amplitude off resonance. Let's put this on a log scale so we can actually tell the difference. What we see for decreasing damping, we get larger and larger resonant peaks. So the amplitude response increases markedly when we have low damping. The largest amplitude of the motion is at a frequency of omega squared minus gamma squared on 2 square rooted. So the largest amplitude actually occurs at a frequency which is not quite omega naught. For small damping, that is gamma much less than omega naught, the maximum amplitude can become very large compared to other amplitudes. And I just want to emphasize here, this is not a mistake. The largest amplitude is not at omega naught, and this is a bit of a surprise perhaps, because, well, the phase change here occurs around omega naught, but the largest peak here is slightly different. It's worth pointing out that when gamma is small, so gamma is much less than omega naught, these two frequencies are practically the same, but there is a slight difference. There's an application of this strong resonance in scanning probe microscopy that's worth pointing out. What you see here is a quartz tuning fork, which has a very high Q resonance, and glued to it is a glass fiber tip, and the tip down here is some few tens of nanometers wide. When this tip approaches the surface, the resonant frequency changes slightly, which gives a very strong change in the phase of the driven oscillation, and we can detect this change in phase and use it to control the height of this tip above the surface. And we can keep the distance between the tip and the surface constant to within a few nanometers by monitoring this phase change. If the phase change were not so sharp, then this technique would not work very well. A slightly different technique is to glue a tip sort of perpendicular to the tuning fork, and in this case they can do non-contact force microscopy of single silicon atoms. So what you see here is an image where you scan the tip along the surface and measured single silicon atoms on the surface using nothing more than a tuning fork and a very sharp metal tip. Let's look at the velocity now, the amplitude and phase of the velocity or current as we change the drive frequency. So instead of looking at xp, we want to look at the velocity, so that's x dot p. So take the time derivative of this function here, we get an I omega popping out to cancel this one, so the velocity is just given by this. Let's extract the phase, so put absolute value signs around Zm, and we get e to the I theta, where theta is the negative of the argument of Zm, and it's equal to all of this if we write it out explicitly. As before, I've written it here for the mechanical system, but we could be talking about the electrical system if we just change Zm to Ze and the mass to the inductance. And theta is the angle between the force and velocity, so now we have some meaning for the angle of the impedance. And it's also the angle between the voltage and the current. So how does this behave? Well, for frequencies much below the resonant frequency, the velocity or current leads the drive by 90 degrees. On resonance, they're in phase, and above resonance, the velocity or current lags by 90 degrees. Again, this is decreasing gamma. The lower gamma, the sharper this transition. The amplitude, similar sort of story. Decreasing gamma gives a higher response in the velocity or current, and the highest velocity occurs at omega equal to omega naught. So it's different to the frequency that gives you the maximum amplitude, which is quite curious. And at omega equal to omega naught, the velocity is in phase with the driving frequency. Let's now explore these angles involved in a phasor representation. What I'm animating here is the force or voltage in orange, and we see the position or charge is in phase with the drive for frequencies well below the resonant frequency. The velocity or current leads the drive by 90 degrees at low frequencies, that is, frequencies below the resonance. The angle between the red and the green, the position and velocity, is always 90 degrees. Now, as we approach the resonant frequency, we see the rate of phase change accelerates rapidly, and then we hit resonance. The velocity or current is now in phase with the drive, and the position is lagging 90 degrees behind, as we say here. If we continue on, we have rapid phase evolution. It slows down again. So for frequencies now well above the resonant frequency, the position or charge is pi, 180 degrees out of phase with the drive, and the velocity lags by 90 degrees behind the drive, as I've written down over here.